Hey, I'm here again.
Hi Niels, welcome.
So I've just been told that you are broadcasting this live the world over.
Yeah, absolutely. And it's our pleasure and privilege.
Excellent. If you have to share the revenue when this goes viral, then.
That's okay. Yeah, so probably we'll wait for another 5-10 minutes before we start.
Yeah, let's synchronize our clocks. I have 5 minutes to 1 o'clock.
Yeah, okay.
It should be 25 minutes past where you are, correct?
Yeah, that's right. That's right.
Okay, I will keep one eye on the clock, but not both.
Nochmal nachgestellt, Uhr? Gestern wie noch falsch. Du erzählst, hier ist deine Audience in der Kamera. Und wenn es dann an die Slides geht, sagst du mir Bescheid, dann komme ich hierher und dann teilen wir den Bildschirm auf die Slides und sind die Slides in groß und wir wechseln auf die Ansicht von oben.
Ja.
Und dann halt die Slides groß.
Okay.
Wenn du dann fertig bist mit deinem Talk, dann schließen wir wieder die PowerPoint und machen es wieder in groß und dann ist deine Audience wieder hier.
Okay, wunderbar.
Das ist ziemlich ein ziemliches Unterschied. Kannst du das mal finden?
Bin ich auf dem Schirm? Also ich werd auf dem Schirm schauen, ne?
Achso, ja. Ja. Moment, okay. Hier musst du weiter nach da. Kannst du ein bisschen stoppen? Ja. Sieht gut aus. Guck noch mal bei dir. Du hast unten, du hast die.
Ja, stimmt.
Ich bleib hier drüben, weil die Maus auf der Seite ist.
Das Ding muss. Okay, ja.
Lass dich nicht irritieren, ich gucke nur, ob irgendwo ein Krümel oder irgendein Wirbel oder irgendwas hängt. Okay. Das könnte dann auch sein, wenn noch eine Nudel an der Nase.
Ah ja. Peinlich. Hi, Kiran. How are you?
Im Laufe der Zeit. Wenn er zwischendurch ausgeht, dann gehen auch aus. Das ist auch ziemlich fest. Good afternoon.
Hi, Virendra. Good afternoon.
Very nice background.
So the sound from your side here is actually quite hard to follow. It's not always possible to make out what you're saying. So I may ask in the discussion afterwards that people repeat, because I may have problems hearing.
Yeah, I guess we'll take it. Hey, Mika.
Everyone to mute.
Yeah. I think webmaster should mute everyone. I can do it. Shall I do it? So, Dr. Tiwari, I have muted everyone now.
Sorry, I just realized that I've been talking to you with my microphone off. Hi, first of all. I just explained in vain that the sound here is not always, from your side, is not always very clear. So I may have to ask, certainly in the discussion, someone to repeat their point.
Okay. So, Dr. Tiwari,
I think
आप दोबारा ठीक से नहीं आ रहा है.
speak up whenever
It's not clear.
You have to put all the headphones.
एग्जिट होके दोबारा आइए.
let us start, Dr. Ram.
Yes. Yeah, please.
Lecture hall guest has to be put on mute, otherwise there's echo.
I understand, and I will do that.
Neil, shall we start? Okay. Very good afternoon and good evening. Namaskar, respected the members of our research council, Professor Tandon, Professor Singhvi, other members. Today the speaker, Professor Niels Hovius, Scientific Executive Director and Chairman of Board of Directors, BFJ, German Research Center for Geosciences, and colleagues, invitees, participating and listening through virtual media, the fourth Diamond Jubilee talk of CSIR-National Geophysical Research Institute. It's our great privilege welcoming all of you today when we have with us a very distinguished seismologist and researcher who is heading one of the best geoscience institutions in the world. You all know that climate, biotic community, human population size, and land use and land cover patterns are changing rapidly on the earth and receiving well-justified attention from scientists as well as from policymakers. One of the great challenges in the post-industrial society is understanding the consequences and feedback of the changes on the landscape. The phenomena of the landscape dynamics within the post-industrial society is considered and is development of the connection between the drivers and landscape changes and management is slowly gaining the importance in society in the view of the impending hazard scenarios, and one of that you all must have seen the consequences and devastation which India has faced in the recent Tapopan tragedy. Today, through seismological studies on a topic, seismological constraint on the climate-driven landscape dynamics, Niels is going to educate us how the seismological and geophysical information can help us in the long and the short-term changes in the landscape using the geophysical observations. I had the privilege of meeting Niels some time back post ministerial discussion during the post ministerial bilateral discussion of India and Germany, and we had agreed at that time itself that we should jointly start with working on the Himalayan hazard using the geophysical and seismological data. At the same time, during our research council, our very distinguished member, Professor Tandon, had also emphasized that CSIR-NGRI should strengthen the studies, particularly on the geomorphology and quantification of the geomorphological changes. In view of that, we started discussing and we have started working and recently also created a group a few weeks back called Environmental Seismology, which connects the seismological observations and geomorphological changes together. In view of that, the today's talk is one of a very important talk for us at the time when we have embarked on a very new and emerging area in geosciences. With these few words and with the excitement of listening Niels, I welcome all of you once again for this Diamond Jubilee lecture, and I hope you all will enjoy it. And I would also like to thank Professor Niels Hovius for agreeing to speak for the CSIR-NGRI on its Diamond Jubilee celebration. Thank you. I request Dr. Rao to kindly introduce, though our speaker is well known.
Thank you, Dr. Tiwari. Thank you very much. And I think it's a great day. We have a very eminent speaker today with us, Professor Dr. Niels Hovius. And I extend a hearty welcome to all of you, because this is a very special Diamond Jubilee lecture. And very briefly, I would like to mention that the CSIR-NGRI, National Geophysical Research Institute, is galloping into its 60th year of existence and service to the nation. So it's a very proud moment for all of us. And I'm very glad to state that this is the 4th lecture in the Diamond Jubilee lecture series. And we are very proud to have Professor Niels Hovius with us today, speaking on a very timely and very relevant topic, that is the seismological constraints on climate-driven landscape dynamics from precursors to outburst floods. And obviously, he'll be touching upon the recent landslide flood disaster that we have seen in Uttarakhand. So I think his talk, I believe, is an extremely timely one. So I'm sure all of you will enjoy the talk and have a lot to learn from Niels. So let me quickly read out a few great achievements of Dr. Niels Hovius. Of course, he is a very established person, and I will pick only a few of the things. Dr. Niels Hovius did his MSc in Physical Geography and Earth Science from the Rijks University, Netherlands, and he has a DPhil, that is Doctor of Philosophy, from the Oxford University in UK. He is currently the Scientific Executive Director of GFZ, Geoforschungszentrum, and Chairman of the Board of Directors. So he's in a very high, very important position, that he's steering the bulk of the geoscience research in Germany today. He is also professor at the Institute of Earth and Environmental Science in the University of Potsdam. So earlier he was at the University of Cambridge as a lecturer from 1999 to 2012. He was a fellow at Churchill College, Cambridge in 2003 to 2012. He has been a visiting professor at several prestigious universities like University of Oslo, University of Rennes, Institut de Physique du Globe de Paris, that is IPGP, and ETH Zurich. He has a lot of achievements. I'll just pick some of the very important ones. He is closely associated with the European Geosciences Union as well as the American Geophysical Union. He has been the founding member and chair of the Geomorphology Division, and he has served in various capacities for the Outreach Committee. He has been a council member and also the Earth and Planetary Surface Process Section Committee. And his academic credentials are very distinguished because he is the founding senior editor of Earth Surface Dynamics, and he has been on the editorial board of very top journals like Geology, Earth and Planetary Science Letters, Earth Surface Processes and Landforms, Basin Research, etc. And he has some very distinguished awards. For example, the Gordon Warwick Award from the British Society for Geomorphology. He has the International Excellence Award from the Helmholtz Association, Germany, the Ralph Alger Bagnold Award from the European Geosciences Union, and the Kirk Bryan Award from the Geological Society of America. He has over 100 publications in very high impact journals and a very large number of PhD and postdoc students. I really will not be able to count, but it looks like It's a pretty huge number. And today, for me personally, it's very heartening that Professor Niels is giving the talk, because as Dr. Tiwari mentioned, we have just started a new group on environmental seismology, and our very first international collaboration is going to be with Niels, and I very seriously look forward to it. And I also look forward to hear him speak on the Chamoli event that caused disaster in the Western Himalaya recently. So with these few words, I would like to hand over to you, Niels, and we are all looking forward to being enlightened by your talk today. Thank you very much. Over to you, Niels.
Thank you very much. Let's first try whether the sound actually works. I don't hear a ring sound. Are you hearing me correct?
Yeah. Very nice.
Excellent. Thank you. Thank you very much. First of all, on behalf of the GFZ, the German National Research Center for Geosciences, I would very much like to congratulate the NGRI on its Diamond Jubilee. The GFZ and the NGRI have been working together for a long period of time. There has been a meaningful exchange of personnel, and we're just entering the next chapter in this collaboration. As Dr. Tiwari has kindly highlighted, informally this chapter started maybe 2 years ago, but formally this chapter is only 2 weeks old. It has an unpleasant start in a natural disaster, but so far the collaborative experience that we have made is a rather very pleasant one. It is a great honor to be given this platform to deliver this lecture. I give this lecture not as a distinguished seismologist. I'm not a distinguished seismologist. My training background is in Earth surface processes, but I have worked with techniques from outside my own field for a long time, and I've been intrigued with the possibilities offered by seismology for over a decade now. And I'm very happy today to be able to present to you some fruits from our forays into seismology, and maybe one day I will qualify as a very distinguished seismologist, but that day is a long time in the future. We will now switch to a different screen setting, but as you can see my entire presentation, and I will be a very small person at the bottom of your screen for hopefully the next 45 minutes. Good. You should now have a full screen view of my presentation. Is that correct?
Yes.
Excellent. Good. Then let me progress straight away to this rather striking pair of images of a little patch in Taiwan. Taiwan is an island on the eastern margin of Asia, exposed to very high precipitation rates and very high rates of crustal shortening. It is eroding at a phenomenal rate, but it isn't always eroding in the same place at the same time at the same rate. This image shows the impact of one single precipitation event in 2009. The red shows you intact vegetation. The gray and blue show you, respectively, exposed rock and debris and water. The only thing that happened, or the most important thing that happened between these two images, was one massive typhoon impact that rained about 2.5 to 3 meters of precipitation over a period of 3 days onto this landscape. The resulting erosion was very meaningful, not only in terms of disturbing the ecosystem and the river system, but also in disturbing society, which has a firm foothold in the lower part of the valley and on the delta of this rather small river. And very importantly, it constituted a mass flux that registered geophysically. Now, geophysics has over the last few decades, developed an appreciation of erosion, the importance of erosion, and has developed a very basic notion of the fact that weather, that climate, is an important driver of erosion. This is first articulated in the work of Sean Willett and colleagues now over 2 decades ago, and has since been taken up as an idea, an important idea, a founding idea in a geodynamic approach to coupled lithospheric deformation and surface processes. In order to have a more realistic and a more forward-looking view on erosion, though, a small set of constitutive equations representing the mobilization of material, but mostly the transport of material in river systems, is not enough. And we need to consider in more detail the relationship between the driving climatic forces and the responding erosional processes at the Earth's surface. And this has been one of my key pursuits for the last 2 decades now. This image illustrates some of the challenges with that. This is a small rain shower somewhere on the Scottish Highlands. And you can see that the conditions on that landscape vary over very short distances and on short timescales. It is therefore very difficult to make systematic observations. You have to be in the right place at the right time in order to get the right type of information. When we try to do this with instruments on the ground, in place, in a classic sense, then very often we find ourselves not in the right place, just next door to where it rains, for example, or we're just there too early or too late. If we do this through remote sensing, classic optically based remote sensing methods, then often the time resolution is too coarse for us to really see the conditions that matter most to the occurrence of the processes in the landscape, because these processes happen fast and they happen very often unexpectedly. And for a while now, for over a decade, I've been trying to develop an alternative approach, an approach that is based on remote sensing through seismological instruments. And this talk will try to give you some perspectives on the use of those seismological approaches and the new insights that we gain from this, the spatial resolution that we can gain, the temporal resolution that we can gain, the access that we can gain to otherwise completely inaccessible destructive processes. And I think this is one of the most exciting developments in the field of Earth surface science and maybe in the earth science in the last decades. At heart is a very simple set of observations. The simple observation is, if I drop a mass onto the Earth's surface, then it will set up body waves, and those will be recorded on seismometers, seismic instruments at some distance. I therefore don't have to be in the place of impact. I can watch this impact from a distance. I can watch the impact of an individual pebble or a boulder dropped from a meter height, and that is the simple seismogram at the base of the slide. And I'll try to move my cursor, that is this diagram. So this is essentially a boulder dropping, bouncing, dropping again, bouncing and dropping again. If we have millions or even billions of these boulders moving down a Himalayan river over an entire year, then we can see that the motion is confined to the summer monsoon season, and that in other seasons, the winter season or the autumn season, it is rather quieter in these rivers in terms of discharge, but very importantly in terms of bedload transport. That basic observation was verified some time ago through a seismic network that was put in place not at all for the purpose of studying surface processes, but instead to study the deep crustal structure of the Himalayas, yielding interesting insights where no insights were sought. Different processes, we've learned, meanwhile, register in different ways on seismometers. Here is the seismogram and the spectrogram of a simple local earthquake. This must be a very familiar picture to many watching this talk. Here is a rockfall event, which may have a similar duration to a local earthquake, but it has a very different waveform, and it also has a different frequency content. A regional earthquake would register over a longer period of time, a period of time that we would also, for example, find occupied by a moving debris flow. But the frequency content is very different between the earthquake in the far field and the debris flow in the near field. And finally, sediment transport occurs over yet another timescale with yet another frequency content. And so all of these processes have a different fingerprint. The fact that they have unique fingerprints allow us to determine the nature of processes, the timing of processes, but also the location of processes if we have a network. And this is a terribly exciting opportunity that we can create for ourselves. Now, the first time we tried to actually see whether this opportunity can be turned into real and meaningful observations was when in the early 2010s we established a small network of seismometers in one of the most geomorphically active locations on Earth, and that is the central Taiwan mountain belt, where there is an enormous amount of mass wasting on an annual basis. And we asked the question, not only what can we see with seismometers distributed across the landscape, but also how can we relate what we see to the ambient climate. And this is now taking a first step towards resolving the relationship between the meteorological or the climatological driver and the geomorphic response. Simply to demonstrate some principles, if there is a localized source of geomorphic source of energy, then we can basically record this over a distance. This is the catchment outline right here, and the gray circles are our instruments. The triangles are our weather gauges. No, the triangles are our seismic instruments, and the circles are our weather gauges. And what you can see is that at a number of seismic stations, there is a signal recorded of a single event of mass wasting arriving at a different time. Using standard migration techniques, we can actually determine a likely location of that source. And then when we compare the locations of a number of these seismologically registered geomorphic events, here with their uncertainties shown in the white bars, then we can see that in a single day with a significant amount of rainfall of up to 60 millimeters per day, there is a systematic co-location between the geomorphic activity and the greatest rainfall rates. This is not a great surprise, but this is essentially a very detailed and quantitative demonstration of that. But we can do more because we have a very high temporal resolution in the seismic record of the geomorphic activity. And so when we look at the rate of geomorphic activity seismologically registered as distributed over a typical day with a typical amount of rainfall, and this is the rainfall in a 24-hour period averaged for many, many days over a 100-day observation period, then we systematically see that the greatest geomorphic activity, shown in the black bars, coincides with the highest rainfall rates. That's the gray curve right here. And there is a relationship between the 10-minute rainfall intensity at the time of the registered geomorphic activity and the rate of geomorphic activity, which has an exponential relationship. This is a quantitative relationship between the driver and the response, which we can use to inform, for example, landscape evolution models, and to evaluate what happens when we change the 10-minute rainfall average in terms of a geomorphic response. So this, if we would do this systematically and in many places, would allow us to start to evaluate the geomorphic consequences of climate change. That is one dimension. And I must say that in that study years ago, we found about 300 events, and all of those events were small, and they really they were small both in size and in terms of their duration. But the most impactful geomorphic events are often larger in size and last for a longer period of time, and they're complex. And I want to show very briefly an example that we published a couple of years ago after the study of the collapse of the caldera wall of one of the major volcanoes in Iceland, the Askja volcano. And what I'm going to demonstrate to you is that rather than talking about individual process events, we should see them as crises. Askja is located in the southeast center of Iceland, in the center of Iceland, I should really say, to the north of one of the major ice shields on the island. And at the time of the caldera collapse, or the partial caldera collapse, there was a large number of broadband seismometers located around the caldera for a completely different purpose. The collapse happened after a period of exceptionally high temperatures with rainfall and significant snowmelt. So we had very wet conditions, which is the climatic boundary condition that is important here. This is a spectrogram of that particular event. The time here is about 1 hour and 30 minutes, or maybe even, no, it's 2 hours, in fact, here. This here is the collapse, the landslide, which you can see has a tail. It has a tail in terms of displacement in direct association with the main landslide event, but you can see a number of subsequent energy peaks across a broad frequency range that is after activity. Very interestingly, there is also activity before the earthquake, before the landslide, and I want to focus in on that in the first instance. I'm going to take this event apart, and I'm going to show you 3 different phases. So the precursor phase, the main phase, and the aftermath. In the precursor phase, what we see are harmonic tremors. They are dominant frequencies in the signal, and we can see a certain amount of gliding in these frequencies. So, for example, here what we notice is that the harmonic tremor actually increases in frequency, and very importantly, it overtakes, or it takes over as the only harmonic tremor, where there are 3, maybe 4 at an earlier point. There is only 1 left, and as that one is left, the frequency increases. And then at some point, the whole system goes quiet. It goes quiet here. You can see this, as quiet as the background, maybe a couple of hours before the event. And then we see the catastrophic collapse of the caldera edge. We interpret this essentially as the acceleration on a dominant patch, or slip patch, that results eventually in the change from stick-slip behavior to continuous slip, and that is followed by a catastrophic failure. And so here we have potentially a precursor indicator of impending pandemonium, of the wholesale collapse of that of a sector of that caldera wall. So precursors are tremendously valuable because they allow you, in principle, to look ahead at things that may come and that may have large consequences. The thing that came was a displacement of an enormous mass. I don't have the numbers here, but what is important here is that we did a force inversion that allows us to show that the incipient motion was located rather at the top of the entire slide complex, and over a period of 1 minute, that mass accelerated down the slope before, over a further minute, it decelerated for the center of mass to arrest right at the edge of the crater lake, where it's clear that a large amount of mass was actually delivered further into the crater, but the center of mass arrested right at the edge. So over a period of 2 minutes, we can follow the displacement of mass, and through this simple force inversion, we can see where motion starts, but also where motion stops, and what exact pathway the mass takes in between. That is the SYN phase. The post phase is also very important, especially in terms of hazard. What we noticed was that after the main landslide, there was a large number of subsequent smaller mass wasting events. And the rate at which these occur at the first instance in the first hour after the main event is very high, and then it quasi-exponentially decays, in this particular case, within a day to lesser and less important rates. The distribution of that activity is rather scattered. We see that little bits of topography here and there in the newly exposed back wall, but also within the deposit, become reactivated and cause further displacement, which may in turn constitute a hazard. So this notion of precursor, main event, and then an aftermath turns this whole thing from a landslide that happens in an instant, as we would see it on a remote sensed, a classic remote sensed image, into a rather more articulated event with different phases. And this is new eyes that we have on a process that people have been looking at for a long period of time. I want to look a little bit more at the promise that is entailed by these precursor events. And this is by no means scoped out in full, but there are tantalizing little insights into the possibilities that we have there. Another insight comes from a network that we ran some years ago in the Swiss Alps in a little fast eroding catchment called the Eel Garden. On this image right here, you see the headscarp of a landslide complex or a rockfall complex that from time to time yields larger volumes of mass in the order of 20 to 50,000 cubic meters. Nothing terribly spectacular, but it's very manageable to look at. Here you see the deposit of an event that came, we verified visibly from this socket right here, around the change from, I think it was 2012 to 2013, but the years I may have wrong. This is the location of that that site that I just showed you, at the base of a rather steep catchment, where that catchment debouches into the Rhone Valley, which is one of the major valleys draining the Alps. Here, this purple triangle shows you the location of a nearby broadband seismometer that we had installed some time before, not for the purpose of watching this particular site, but as part of a network that allowed us to look at the activity within this entire catchment. And so this was really a lucky strike. The distance between that instrument and the top of the scarp is about 150 meters. And this allows us a very close look at what happened. Here is the seismogram of the main rockfall. You can see the breakaway phase, you can see the rolling phase, and you can see a restart of the debris on the scree slope. This is that same thing lit out. I'm very much interested in the hour before, which shows background activity with minor disturbances, but then these single peaks in activity right here. And if we zoom in, then we see that these are single pings, and they look just like fracturing in concrete in a lab experiment would look. So we interpret these very short signals as the fracturing that occurs in the rock mass. Because we have data from only one station, we cannot actually assign a particular location to this fracturing. But what we did observe was that in the run-up to the catastrophic rock wall failure, here on the right-hand side of the timeline, there is an exponential increase in the rate of occurrence of these little cracking or fracturing events. And so there's an indication here that basically the cracking or the fracturing is preparing the rock mass as a whole for its catastrophic failure. Again, something that if we have instruments in the right place can be used as an early warning. Now, the episode that I just showed you is located right here. If we go to the upper diagram and to the blue line, which shows you the cumulative rainfall, you can actually see that this happens during an entirely dry period. But a week earlier, there was an exceptional warm period. Red is the temperature right here for the winter conditions, much warmer than normal conditions in winter, with again snow melt. And a large amount of rain, about 30 millimeters of rain. This is a rather dry spot in the Alps, and so this is truly exceptional for this time of year. And what you can see is that when this little weather event actually happens, and now we look at the green line right here, which is the rate of cracking that we detected at this station, we can see that the rate of cracking actually increases in a quasi-exponential fashion, but then it stops and it goes back to a background rate. So there is some cracking, but it's nothing special. And if for some reason, and it's not related to climate at all or to weather at all, a week later this picks up, and then we have a successful preparation for catastrophic failure, the event that I just showed you. And so you can see that the failure that occurred here, which normally would be attributed to the weather conditions that are flat here, colder and dry, in fact is related to the conditions as they were a week prior, when it was exceptionally warm and exceptionally wet. And so there is a delay, there's a lag between the climatic or the meteorological driver and the geomorphic response, which makes it more difficult to analyze relationships between climate and erosion. If we zoom out in the same landscape, then we can learn some other lessons. This is now looking from the back wall of the same tiny catchment, the Eel Garden. I just showed you data from the location, which is right here, where my cursor is pointing now. You can see that this catchment is very simple. It has a single trunk channel, and it is surrounded by very steep rock walls that crumble at a high rate. During a very wet day, the wettest day of 2011 in the summer season, we made the following records, and I'll show you three stations. I'll first show you a station beyond the catchment on the high mountain ridge, but not immediately located anywhere near a channel. What you can see here over a 24-hour period is meteorological activity. There's an afternoon rainstorm right here. And what you can see at a lower frequency is human anthropogenic noise. You can essentially see the breaks that people make, the breakfast break, for example, or the lunch break in Switzerland, and people all down tools at the same time. This is universal time, so you have to add 2 hours at 12 o'clock. And then they basically break for lunch for about 50 minutes when they start up everything again, and then it trundles on until the evening. So anthropogenic noise is a very important component of these higher frequencies, as you well know, and it's a demon that we have to slay. If we go to a station which is in the upper part of the catchment, located quite close to the channel, then we see a completely different picture. We still see the climatic or the meteorological activity at higher frequency, but at lower frequencies, we see sustained energy pulses, and I'm particularly interested in this pulse right here. This channel is very important in generating debris flows, and here we see 1, 2, 3 pulses of debris flow activity in action. For a shorter period of time, 800 seconds here, located in the early part of this record, this is the seismogram. At the start of the event seismogram is this short pulse right here, which is also registered at stations that are far away from the channel. It is a rockfall. There's a second rockfall here that is hidden in a rather more complex and long-lasting waveform, to which I'll come back. This is the location of that first energy pulse. It is a rock failure in the upper part of the catchment. And that rock failure it produces material that reaches the channel. And as it reaches the channel, it reconstitutes into a flow. That flow propagates down the channel. And as it scours the bed, but also the banks of the channel, it manages to destabilize the channel banks in part. And this is the second rockfall, hidden and already pointed out to you here, which is co-located, or it's located right next to the channel. And so what you see, in fact, in this particular case, is a rockfall that triggered a debris flow, that triggered a rockfall in passage, bulking out and then propagating down the channel. And so what we find here, and again, this is not surprising, but it's beautiful to demonstrate that this is actually happening rather than just us speculating about it. There's a two-way feedback. It's a feedback from the rock walls to the channel and from the channel back to the rock walls. So this is an important concept. Now, these processes that I've shown you so far could be considered as stochastic. They are the processes that we expect in the landscape. Sometimes they're small, sometimes they're large. They have known size frequency distributions, the frequency of which is forced, for example, by the rate of rainfall or by the rate of tectonic forcing. But there are exceptions. There are things that happen in landscapes that don't fit in the normal picture, and outburst floods are one of them. This is an image from 2016 from the central Nepal Himalayas, the Botikoshi Valley, after a glacier lake outburst flood scoured this valley, filling it with up to 20-25 meters of water. It's a small version of what just happened in the Dhauli Ganga. This GLOF, this glacier lake outburst flood, happened to occur in an area that the previous year had been affected by the Gorkha earthquake. It is in the extreme eastern part of the earthquake region, and we had gone there to install some broadband seismometers to look at the velocity structure and the evolution of characteristic velocities in the shallow subsurface in order to study the damage and healing during and after earthquakes of the near surface rocks for completely different purposes. This network was dissected, was hit by the glacier lake outburst flood, and so very luckily again we were able to take a very close look at this outburst flood that we didn't expect to pull. Here are some pictures of the effects destroyed hydropower facility, a settlement that is affected by the mass wasting right above the active channel, roads that were here that are no longer there. These are images that are identical to the ones that one can find now in the upper Dhauli Ganga. If we take the information, the seismological information from our local network, and we look for a location of the start of this event, then our network tells us that we have to look in this particular direction. That is the azimuth, but we don't know exactly where we have to look, simply because the source, the starting point, is acentric to our network. So we don't have much purchase on the exact location. But if we look in this direction, then what we find is two glacier lakes. The big one is the eye-catching one, but I draw your attention to the very small one, which is about, 250 meters long and about 80 to 100 meters wide. It's a very small affair, by all means. The picture I just showed you was before the outburst flood. This was a satellite image taken not so long after the outburst flood. And what you can see is that the lake has drained. It has filled with a large amount of sediment that has come from underneath the glacier tongue, which is located right here. And the terminal moraine, which is here, has been breached. And you can see that the channel has been scoured downstream. So this, in our interpretation, is the starting point for this event. It's a starting point with a very small volume that had rather catastrophic consequences, and I'll try to explain why these consequences can be so large from such small beginnings. The outburst flood traveled down this channel right here. It hit the main channel at this particular point, and it passed by very close by four of our seismometers. These are the records from these four seismometers, and as the flood passes, what you can see is a very steep front, a rather uniform signal, and then a higher amount of energy at a higher frequency, and then a long tail. And we can see the same picture at all four of our sites. We can see that the front travels at a speed of about 7.9 meters per second, and it has energy at a characteristic frequency that we interpret as water. We see a second pulse right here, which travels at 5 meters per second. That is considerably slower. But it is this first pulse that I first want to consider just a little bit more. these 8 meters per second are substantially faster than the river would flow under normal conditions. There is water in the river, and then there is this bore of water that charges down and it overruns the river. As it does so, it actually recruits water. And so the bulking in terms of hydrology of this flood is simply because the initial outburst flood eats the river that it overruns and it recruits water from it, increasing the flood volume quite dramatically, so that the water depth is indeed up to tens of meters, and so that the water has a capacity to mobilize large material. Those water amounts are rather exceptional. These are 4 hydrometric stations with the likelihood distributions of the floods that occur under normal meteorological conditions there. And you can see that the 75-year return flood here is picked out by this line at these various stations according to long-lived station records. These are measurements of the discharges in the upper part of the system that are associated with a glacier lake outburst flood that I just showed you in 2016, but also a slightly larger one in 1981. And what you can see is that these discharges sit completely outside of the normal envelope. They are black swans. They are events that sit simply not within the normal magnitude frequency distribution. And it is those events that have a very costly impact on the infrastructure, on the population, but also a very intense impact on the geomorphology and the landscape dynamics in these high mountain environments. We have much more detail on that, but I just want to explain some of that impact in this one single slide. Here we see the water bore. Here we see a second pulse of energy with a slightly different frequency, which we normally associate with bedload transport. And what you can see is that the bedload moves at about a velocity that is 60% of the water velocity. This is very interesting because what we find in physical experiments in the laboratory is that bedload moves at about 0.6 of the velocity of the water that moves it. And so in reality, in a big flood that we cannot gauge in any way because it is too destructive, but with seismometers we can actually make observations from a distance, is what we find is that the behavior is identical to that in a perfect setup in a laboratory. So we can actually develop a meaningful and simple physical model for this flow. And the separation of the bedload and the water is actually fundamentally important to the potential for real damage that such floods have. The separation is the result of the fact that a lot of the bedload is actually recruited at a pointer over a short distance and is then traveling at a lower velocity, which basically means that the water moves ahead of the bedload and retains its capacity to mobilize more material simply because it doesn't have a lot of mass to transport from further upstream. And this means that the water is exceptionally capable of moving large pieces and mobilizing large amounts of sediment and rock mass at its front. And that is where the real damage actually occurs. Substantial damage also occurs because these flows are capable of moving exceptionally large bedload particles. And that is the second part of the story. Now, as I already said, the events in the Botokoshi in 2016 were not so dissimilar to the events that have occurred on the 7th of February this year in the Upper Daliganga catchment. And on the Sunday that this catchment was hit by this disaster, I climbed into my email and I wrote to Virendra Tiwari, reminding him of a discussion that we'd had 2 years prior at this meeting in Bangalore, where we talked in theory about a collaboration. I remembered that the NGRI had instruments in the Uttarakhand province, and I thought, let's see whether there is an interest in the records from these instruments. Are these instruments still in place, was my first question, and things kicked off from there. I was interested in particular about this in this network because from the corner of our eyes in 2016, we made the following observation. The information I showed you, the spectrograms I showed you for the GLOF in 2016 were from stations very close to the channel. This is a spectrogram recorded at a station 25 kilometers from the GLOF source. And what you can see is the GLOF right here over a period of significant length. This is the equivalent spectrogram for a station 60 kilometers from the GLOF source, and still you can see the GLOF recorded over a considerable period of time, over a considerable range of frequencies. So there is a suggestion here that these GLOFs are visible not only in the near field, seismologically visible, not only in the near field, but also in the midfield and possibly in the far field. Preston Cook at the GFZ has trolled records and has found a few examples. I want to show just one of them to you. This is a GLOF that happened in Bhutan in 1994. And this is the seismic record of that GLOF. Again, you can see an articulated event with a steep start and a long tail with characteristic frequencies in the single-digit hertz range. And so what this promises is that we can see these events over a distance. If we have instruments in the landscape and we pick up such signals at an early point, then there might be a promise of effective early warning through a seismic network. This is the NGRI seismic network in the Uttarakhand province. This is the starting point of the GLOF. This is the 7th of February, and the green line is the trajectory that GLOF actually took. You can see there is one station nearby. There's a larger number of stations in the surrounding, and so the opportunity we now have is to see how that GLOF registered on this network and to test whether that network actually allows us to first of all identify the flood at an early point and then to locate it and track it at an early point. We're in the process of doing this, and so I can only show you very preliminary results about which I'm quite excited, but this is not a finished story. It will, however, be the end of my talk. This is a satellite image taken shortly after the disaster. You can see here a triangular wedge failure high on the flanks of Nanda Devi. You can see the air-blasted dust from that dry mass movement splashed over the snow-covered landscape. You can see a channel right here which has been affected. And that channel passes by the near field station AUL, from which I will show you some data. This is a DEM difference attempt at estimating the volume of the initial landslide that was at the start of this event. It's a triangular volume of about 25, maybe 30 million cubic meters, which is a very respectable size landslide to all accounts. Here is scattered, this area with scattered topographic change right here, which is maybe 8 to 10 million cubic meters, was affected by another mass movement earlier in September of 2016. It's not known how much ice was involved in that and how much rock was involved in that. Same true, in fact, for that wedge failure right here. But it plays a role in the composite event. My aim here is not so much to review in detail what that composite event was like, but rather to see what other evidence we have. So I showed you the topographic change due to the event, the mass racing event at the start. Here are some hydrometric records that allow us to track the subsequent flood. This is the position downstream of the flood front over time, and we can see that, yes, it travels downstream over time at a velocity that decreases as we go from the highest part of the catchment to the lower parts of the catchment, but it is incredibly respectable at more than 20 meters per second. This is the speed a car travels on a motorway if it doesn't go too fast. And you can also see an estimated peak height of that flood, which in the upper part of the catchment was several tens of meters, but then 60 kilometers downstream had already attenuated to less than 5 meters. And so further downstream, it is not a very impressive flood, but it may still convey an impressive volume of water, an impressive volume of sediment. This, in the upper part of the catchment, the upper, let's say 40 to 50 kilometers of the catchment, this is where the destruction was located and where we would have the greatest disaster potential. Now, I want to show you some seismic data from the station AUL, which has been shared by the NRG with us, and I'm very grateful for the privileged access to this rather unique data set, and I really look forward to working with more of that data. I won't personally do that work. I'm no longer in the position to be actively engaged, but there is a group of very enthusiastic people at the GIFTSET who are looking at this data now. Rather than showing you the timeline, this is UTC from 4 o'clock to 6:30. In all its gory detail, I want to focus on the frequency range that really matters. So I'm going to show you a cutout of this event, going up to the 10 to a frequency of 10 hertz. So this is a shorter period of time, around 5 o'clock UTC, stretching into 6 o'clock UTC. And what you can see is a very steep front right here, which is the landslide happening right high on the slope. We can see a tail that lasts many minutes with a creeping optimal or maximum frequency, which we interpret to be a debris flow in the upper part of the catchment that ensued immediately after the landslide. And then we can see the flood passing by the station with a higher characteristic frequency. And so in here, implied, in fact, is a change in how this flow is constituted, where the lower frequency suggests a higher sediment concentration, perhaps a non-Newtonian rheology, and the higher frequency suggests a lower sediment concentration and perhaps a Newtonian, so a normal flow behavior. If we take data from several of the stations in this network, they're located, they're shown here with the single letters, 5 stations, then we can actually, and this is work that Rajesh, and sorry, I don't know your surname, has done at the NGRI. And we find that the location of the landslide, actually, that we determined with the seismic data, coincides with that of that we have determined independently from satellite imagery, and the satellite imagery is highly accurate. The seismological location actually coincides pleasingly with that, and so in principle we can see the initial event. That's good. That's a good start. But what what we should be worried about is not that landslide, because it happened largely in uninhabited terrain, but the disaster was largely played out through the subsequent flood and its propagation downstream. And so we're not so much interested in locating this particular bit right here, but we're interested in locating the tail, in tracing the tail, and in determining whether there is a tail of this landslide at all, whether this landslide results in a subsequent debris flow and then a subsequent flood event further down the system. Yeah, and so when we look at a station not too far away from the channel, in fact, this is exactly what we see. We see the landslide happening. I've already shown you this, the debris flow happening, and then basically as the debris flow loses much of its weight and translates into a normal, perhaps Newtonian flood, we kind of lose track of it, but not entirely. We can still see it if we squint, and then as the flood approaches the station, we pick up the signal again and we see it pass by the station and then trundle away in the distance. So here there is a very clear record of this whole event. If we go to another station slightly farther away from the channel, and sorry, I don't have absolute distances for you, but here you have the degrees and you can do your own mental maths, at least get a ballpark figure. We can see the landslide, we can see the initial flow, And then if we look really carefully, maybe we see the flow right here, but it becomes much fainter. It becomes much harder to actually to recognize it. At this station, TR&R, which is yet farther away, again, we see a landslide, we see the debris flow, and there is activity here at the frequency range, in the frequency range 1 to 5 hertz, which we don't see before, but we have not much of a time record here before. We have not seen that yet. So a meaningful comparison is between this window right here and this window right here. But the suggestion is that there is activity here that we don't see here, and that activity isn't the same frequency range that we saw is occupied by the flood event at near stations. If we go into the far field at station TUN, again, we pick up the landslide, again, we pick up the debris flow, but we don't really have much evidence anymore of the subsequent flow event. And so within this network, we are expecting to find information about the maximum reach of the information, the seismically recordable information that this flood emits, the signal of that flood, so to speak. And with that, we will be able to find the limitations of teledetection. Now, we can be slightly more precise, and this is really now coming to the end of the talk and looking forward a little bit at where we can go next. So here we zoom in again on the AUL station, now over a very limited frequency range, and what we can see is that, in fact, this is the bit of the event that we're really interested in detecting and locating. It's not the landslide, as I said, that's easy, and it also doesn't typically impact direct on civilization. This is the bit that does all the damage, the flood. And so this is where we need to apply our force. And what you can see is that there is a mode to this frequency domain, which is located, let's say, between 1.7 and 2.3 hertz. And so if we now filter the signal at that in that frequency range, and we plot that as a function of time, then basically we can see the landslide. Again, this is at the station AUL. We can see the debris flow, and then what we see is that there is a lull in the activities, but then the activity picks up, and in this frequency range, there's a lot of energy carried as the flow approaches, passes by the station, and goes into the distance. And it is this point, if at this point, basically, this line would continue downward, then one can actually learn, okay, now this event does not propagate significantly downstream. Rather, it has dissipated all its energy. But if instead we find that there's an inflection and the energy picks up again, then we might say, okay, now look, here's an indication that something is still afoot, something is still moving, and it's coming towards us. We see this in various stations. We see the landslide, we see the debris flow, and then we see an inflection. And we can see that even here at GHA, which didn't look very promising at the start, we have that increase in this very narrow frequency range. And even farther afield, we see something very similar. And so this, I think, is where there is real promise. It is looking in a more articulated and in a more sophisticated way at these signals, filtering them at different frequencies, trying to find those frequencies that contain relevant information, and then see how the energy content evolves over time. And it is these inflections that I think should, in future, maybe allow us to sound alarms, to define alarms. This is what I would envisage that we can work with next. So this is me thinking on my feet with data that arrived with us just 24 hours ago. I very much look forward to the next phase of that exploration together with the NGRI. I look forward to trying to scope the feasibility, but also the limitations that we might have with that, the development of an early warning system. If we succeed in this effort, then we can deliver something that has true, meaningful value, not only for the population in the Dhauli-Ganga Valley, not only for the population of Uttarakhand, not only for the population in the Indian Himalayas, not only for the population of the broader Himalayas, but for the population of high mountain areas that are exposed to lake outburst flood and other catastrophic floods worldwide. And with that, I would like to thank you for your attention. I will switch my screen to a short summary. I will not go into the detail of that. You've heard me speak, and I am very excited about hearing your questions. Thank you.
Thank you very much, Professor Niels. That was a very enlightening talk. And maybe you need to mute Niels for a while.
Okay, yeah. I've now switched my screen back so that you can see more of me.
Yeah, that's better. Yeah. So thank you very much, Niels. I think that was a very enlightening talk. And for most of us, it clearly shows how using seismology, an entirely new dimension of monitoring hazards can actually be initiated. And it's very interesting to see that seismic networks can actually remotely sense the major hazards on surface, like the landslides, floods, and globs. So this is a very exciting prospect, and I think we have, in a very timely manner, come forward for a fruitful collaboration with GFZ, between NGR and GFZ, and we all look forward to this very useful collaboration in the years to come. Now, I would like to invite a few questions. If there are any questions from participants, we can take a couple of questions. Yeah, we have Professor Singhvi, who is a very distinguished scientist of this country, and he's a member of our research council. So, Professor Singhvi, please go ahead with your question.
Thank you very much for a very interesting talk. I have some few questions out of my ignorance about it. Firstly, where does your signal originate within a landslide? Or at what point signal originates? Because your spikes are too sharp. I would have expected them to be much more diffuse in time.
I showed this. The sort of question is, where does the seismic signal in a landslide originate? I showed this Askja, this Icelandic saga, I called it, where I showed you very briefly the seismic information we have about that large landslide. What I showed you was that the activity, and therefore the initial source of seismic signal, was located at the top of the landslide. But then as the mass migrates and disintegrates, the source becomes larger and changes its location. So where is the source of the landslide signal is a question that depends on many factors. I can't give you a generic answer to this. I must say this depends on the individual case. However, what you very often can see is that there is a catastrophic start to this whole thing, where the mass first mobilizes through a failure in tension. And this was embedded within the data that I showed you for that very small Swiss catchment, where you can really see a failure in tension at the start, releasing a large amount of energy, and then the event becomes more complex. So very often it has a very simple start, which we see as this very steep rise, and then after that it becomes more complex.
Can I ask one more question? Can I ask one more question?
Yes, please. Yes, sir.
We often talk about geomorphic thresholds. So you have to really prepare a site for a landslide to occur. So when you talk in terms of meteorological drivers, are we not ignoring what has happened 50 years for the material to be prepared for transport? So how valid is your correlation with the meteorological drivers? Because that is the final straw, but the material is being prepared, and that's a function of climate, rock type, and I did not see anything being folded into that kind of calculations or your interpretations so that we can really predict properly. So how do you talk into the thresholds?
Yes, you're exactly correct, and thank you very much for this question. It's a very important question. I did not claim to be able to resolve the root cause of these of such mass movements. Rather, I focused on the timing of the actual event and its relation to the meteorological boundary conditions. Yes, the root cause very often is somewhere in the deep geomorphological or even in the undeep geological past. It has a geomechanical component, it has a geochemical component, it might even have a biological component, and that is all not captured by the seismology in the way that I've shown you. We can maybe look at velocity characteristics of sites in order to track that in a bit more detail, but I didn't talk about that today. And so rather my objective in this particular talk was to analyze the relationship between the conditions that actually set off the motion and are not the deep cause of that motion, and the conditions immediately before. And those conditions immediately before are just the last and seismologically visible part of a longer history to which you allude. So you're exactly right, but it was not entirely the purpose of my materials here to try to probe those root causes.
Thank you so much.
Thank you very much, Professor Singhvi. Anyone else would like to ask? May I request Professor S.K. Tandon, perhaps you'd like to make some comments?
It was a pleasure to listen to this talk. We had been looking forward to it. And I think it's a new window of opportunity for the NGRI and for the country now to be able to use the data that is available. I mean, it is in some ways most revealing, to me at least, because I was not familiar with this, neither the literature nor the application. I mean, apparently it's been going on for more than a decade now, the application of seismology to the Earth surface processes, and in particular to hazards like GLOF, landslides, and so on. And the fact, I mean, what is most heartening this evening is the fact that data on the recent event of 7th February has moved so much forwards already. So this is something that I'm going to look forward to. There's only one minor curiosity question. It's not a question, basically. See, there is this, when this failure took place, particularly the 7th February one, there was the issue of a huge mass of ice and debris, collapsing together, actually. Now, does the seismic signal offer any opportunity of trying to figure out, what is the rock mass and what is the water and content and what is the ice?
Thank you for that question. You're asking about the seismological, the opportunity offered by the seismic data to probe the rheology of this event. I've shown you one aspect of this. I've shown you a shift in the dominant frequency between the early part of the flow event and the later part of the flow event, which I very tentatively and speculatively related to a loss in the solid content, a reduction in the solid content of that flow, and maybe a transition from non-Newtonian to Newtonian behavior. That is informed not so much by what we see in the data from the one station AUL that I showed you, but that is informed by earlier observations that we made from a number of stations in the Swiss Alps that were located very close to the two events and to the river. Unfortunately, I think that in this particular case, the density of the stations and the locations of the stations that we have at our availability is insufficient to probe the detailed mechanics of this event in too much detail. You ask a very pertinent question: how much rock was there involved and how much ice was there involved? It's not only in the initial landslide, but it's also how much rock and ice were there involved once the initial landslide hit what likely was a sizable earlier deposit that resulted from the collapse of a glaciated flank of the Nanda Devi massif. I'm afraid that in this particular case, we will not learn all that much about the the mechanics of this event, but this is one of the two lines of pursuit that we have at the moment to try to extract as much insight, mechanistic insight from the data that we have. But I showed you the most proximal data, and that is the record. That's the only record that we will have to work with. If we are to more systematically probe the mechanics and mechanistics of such events, then we will have to bring our instruments closer into those locations that are most likely to produce such events in the future. I have rather more hopes for the regional approach, where we should be able to see what kind of network, instrument network, is actually going to allow us to reliably detect and warn at an early point in time for the occurrence of such events. This is where I think the true value of this particular opportunity lies. Although we invest a lot of effort at the moment in the mechanistic study, I think that ultimately we're going to see the biggest increment of knowledge gain in the more regional approach.
Thank you very much, Niels, and thank you very much, Professor Tandon, for your very useful remarks that you made. In fact, you are very right in saying that a new dimension has opened up for NGRI in environmental seismology to address some of these surface processes and hazards. In fact, I'm very glad to tell you that we have a major plan to develop an early warning system in collaboration with Niels and his team. And I think that is going to be extremely useful, both from the scientific and societal point of view. So thank you very much. Maybe we can have one last question. Anyone else? Rajesh, you would like to say something? Rajesh Srekapalli is one of our most active researchers in environmental seismology. You have some question, Rajesh?
No, sir. It's clear to me. Hello? Am I audible, sir? Yeah, yes, it's clear, sir. I mean, no questions from my end. It's clear to me.
Maybe you can say a few words about the location that you could do.
Yes, sir. Location. We have tried in two different manners. So first, we try to find out the location by appropriately assigning some velocity values. So we, with the surface wave velocity ranges from 2000 to 36, I tried. Wherever it is 2400 velocity, we find the best fitted location with the satellite imagery. And in addition to that, we have trialed another experiment, sir. Likewise, we have changed the time window of the seismic trace, where we have approximately coming to the exact location for a time window between 4 hours 52 minutes 10 seconds to 4 hours 52 minutes 35 seconds. So we are expecting the event is occurred in between this time.
Yeah, I think that's fantastic, because it shows that the precise seismic traces that we have on various stations would enable a very precise location as well as the origin time of various events that happen in the sequence. Yeah, thank you very much. Thank you, Rajesh. And Dr. Tiwari, we would like to make some ending comments. And then we should thank Niels for this excellent talk.
First, I must thank once again for enlightening us such a new area and the prospects of working with the seismological data regarding to the quantification of the near surface processes. Means I have one curiosity, like we are able to now put the energy amount of the energy quantification for any blast or any kind of the dynamite based on the seismogram. What else will be possible to hire the possibility of estimating the energy of the such slides? Like suppose a slide happening at from the 1000 meter height and a slide happening at the 500 meters high. So the energies will be different, even the masses are different. So same mass will have the different energy as well. So how do we really normalize this?
Thank you. you're asking about a part of the the processing and the understanding that I'm less familiar with. What we propose to do is a force inversion, as I showed you for the Askja, the Icelandic example, where we saw the mass starting to move very high in the landscape and then moving down and arresting in a 2-minute period. That for that particular event and for a number of events, and this is approach that was first mooted by Ekström and Stark some considerable time ago for very large landslides. We were able to actually calculate the total mobile mass and the energy rather in a way that is within the right ballpark as we know it from other observations. And so if we manage to do this also for this particular event, then we can go beyond the very simple calculation of, okay, now here's a total volume, say 25 million cubic meters. It starts at an elevation of 5.5 kilometers. It drops 1,800 meters. So the total energy is X. Yep, someone else has already made that calculation. It's a very significant amount of energy that exceeds some of the early atom bombs that were thrown on humanity. So we can do better than that. The relevant question is, okay, now how much energy is in fact dissipated on the way down? How much energy is dissipated in friction within this mass is scattered because the mass distributes is absorbed in debris, rock contact, and so on. And so we can ask much more, or we can answer much more precisely how much energy is likely to have been delivered at the valley floor. And this is a relevant question because this is where we expect that a lot of the melting has happened of ice debris that was already in place since 2016. We don't know exactly how much that was. But with the energy that is available at that point is basically an upper limit for the amount of melting that you can do. And this is a vital piece in the puzzle if you want to understand why this landslide so effectively turned into a flood that was so ugly and so big. Yeah, it's not only I gave you a part of that picture in saying, okay, now the flood, once it started to moved so fast that it overran the river and recruited water. No, an important part of that initial flood was simply through melting during the February 7th avalanche, and as that avalanche impacted on ice debris on the valley floor. And so this is a calculation that I'm hoping we will be able to do with data from the network. I haven't seen the result of that calculation yet. That relies on a good velocity model. I'm pleased to hear that Rajesh has tested velocities and has come up with a velocity that actually gives us a location that makes most sense. So we have a good constraint on that velocity, and I think we're now in a good place to start that force inversion. I'm looking forward to the results, but I can't give you an answer just yet.
Yeah, thank you very much, Professor Niels. Yes, probably we can wind up the session, but I would also like to thank all the scientists and all the colleagues who have joined us online and attended to this very important, useful talk. I must also place on record our appreciation and thanks to Dr. Sri Nagesh and his team who have established this very important seismic network in Uttarakhand, which has actually made this entire collaboration and this entire exercise possible. So thank you, Dr. Sri Nagesh. I think that was a very important and wonderful job that your team has done in Uttarakhand. So with this, I think we can wind up this talk. So thank you very much, Niels, once again. I think we really enjoyed very much and we look forward to this collaboration in future. Thank you.
My pleasure. Thank you again for the invitation. Happy birthday. And I very much look forward to discovering together and publishing together.
Yeah.